All right, so here we go for our third lecture in this series of dynamics stuff. Today we're going to cover two topics. We're going to look at the idea of relative motion. The idea here of relative motion is basically what if you have one piece that's moving and that piece that's moving is sort of looking at another piece that's moving, how fast does it look like that other piece is moving? So a classic example of this is that if you're riding in a car driving, let's say 50 miles an hour, and then someone comes and passes you going 100 miles an hour, how fast does it look like they're going? Right? Well, if you were standing still, it would look like they were going 100 miles an hour. But since you're going 50 miles an hour, they only look like they're going 50 miles an hour relative to you, right? It's why you can drive where, let's say, you're driving at 60 miles an hour and someone else is driving at 60 and a half miles an hour. It looks like they're just creeping past you even though both of you are going really fast, right? Well, that same idea can be extended not just to one dimension. It can be done in 2 or 3 dimensions as well. The idea that you can describe a relative motion. And to get into this, I want to kind of describe this first of all with 2 displacements. Okay, so let's say that I have a particle that's in one position here, and this particle that's in this position here might move through some, I'll use a little vector here that describes a motion of that particle. And I'll call this, this will be like particle A. Right, and so the motion that happened here, I'll call it R sub A. That's the variable it typically uses here in this book to describe a, kind of a displacement or a motion, a distance. All right. Well, imagine if there's another particle that's somewhere else. So let's say there's another particle that's down here, and it starts right here, and it goes through a different motion. Right. So let's say this one down here moves from. I won't make it go horizontal. We'll make it go a little bit down. Say like this. Okay. This is particle B. And so we'll call this R sub B. All right. I want to show you something that I think is kind of cool. I'm going to draw another vector here that kind of shows you what the initial separation was from A to B. Right? How far was B from A? Right? That's initially, right? So that would be a vector that you could describe like right here. So this is our, maybe I'll just label it initial separation. From A to B. Okay, well, what is the final separation? I'll tell you what, I'm even going to lengthen this vector a little bit more just to make it real obvious, kind of make this figure look better. Make it that long. Okay. Well, the final separation, you look at the end of the 2 changes in position that happen for A and B, and you'll find another vector that extends from here out to there. Okay, so this down here was R sub B. Okay, and so this is at the final position. This is our final separation. All right, and you might say, okay, fine, so what? Well, I want to show you this, and it is, I'll show you a couple of construction of vectors, because remember how vectors add. They add with kind of a head to tail kind of an arrangement, right? And so let's think about adding a few things together. I'm going to start with, what if I take my initial separation, all right? So I'm going to take that vector right there and copy it. Put it right here. And then I'm going to take my final separation. I'm going to start it at the same location. Okay. So this is one of the nice things about having a tablet. I can make those exactly the same, right? So I make those exactly the same. Over here we have the initial, right? This is how far apart they were initially. This is how far apart they are finally. Okay. So what's the difference between the two? Right? If you think about the difference between the two, you have the initial plus something is going to equal the final, right? So there's another vector that I could put in here that is sort of this, other thing. What would that thing be physically if you were to kind of interpret that physically? Okay, it's kind of, how much more would you have to move beyond how far they were separated initially? It's how much further are they separated now, right? That is kind of the difference between the two separations. That's what I added right here. This is the difference. Okay. Well, so far so good. Well, let's look at another construction. What if I take my two vectors RA and RB? All right, so I'm going to do those up here. I'm going to then copy them just like I have them over here. I'll take RA, copy it. And I'll take RB down here, copy that. Okay. And one of the things that your book has in it is a formula that says the displacement of B, right, R sub B, is equal to R sub A plus R of B relative to A. Okay. So what would that look like in terms of the drawing of these vectors? Okay, you might be shocked to find, or you might not, that I can take this vector right here that I just drew, copy it, and what do you find? Okay. The point I'm making with this, and I know it's a little bit obscure, but the point I'm making with this is that when you have two particles that move in kind of two different ways, right? You can find the motion of one relative to the other just with that formula, RB is equal to RA plus RB relative to A, right? That describes it, and ultimately that R of B relative to A is really just giving you the difference between the initial separation and the final separation. Does that make sense? So, the difference sometimes matters to you. It might be how much further apart are you than where you started, right? So that's, that can be done with this very simple formula. All right, and this is a very useful formula, this one right here. If you stipulate, you basically say, I'm going to assume at least for the first part of this course, we're going to assume that the coordinate system attached to any of these particles is not rotating. We're going to assume that it's not rotating. And if it's not rotating, then your unit vectors do not rotate. And if your unit vectors don't rotate, we don't get into the interesting calculus that we had to do last time. If the unit vectors aren't rotating and accelerating, right, then you can just basically sort of ignore those unit vectors. Okay? So what you're going to do with this construction here of RB is equal to RA plus R of B relative to A is just take the time derivative. So if you just take the time derivative of this and you say R, the motion of B is equal to the motion of A plus the motion of B relative to A. Right, and what's another way to write this with these time derivatives that I've written above them? Okay. The time derivative of a position vector R sub B is a lot of times just written V sub B. Why is V? It's V because it's a velocity. Okay. Well, what happens now if I take time derivatives of that expression? What do you think that is? We can replace that variable with A because A is a symbol we use for acceleration sometimes. So, and again, these are all valid while we do not have rotating coordinate systems. Okay, so that's one of the things that we've specified to have these. This is for non-rotating coordinate systems. Okay, there shouldn't be. Thank you. The question was, why did I put dots on the A's? I was just getting too eager. That's all. Shouldn't be dots on the A's. If you put dots on the A's, what do you get? Okay, that parameter, if you take a time derivative of acceleration, is called jerk. And I think we mentioned that very first class. But jerk is not while it is something that is sometimes interesting for engineers to study, it's not necessarily a key part of this class. So we're going to stop at acceleration. Okay, so that's for non-rotating coordinate systems. You want to do an example? I knew you would, so I brought one. All right, what you have here is a particle A that is constrained. Let's say it's hanging on a little rod or something, so it's constrained to move in an arc according to the radius r and position theta. Okay, throw just a little tiny kink in there. I'm saying theta is positive clockwise. All right, at least to how the how I have it defined in terms of the parameters that are given to you. Okay, and maybe I'll mention this real quick. There's a lot of times where there's two different kinds of problems that you might encounter in dynamics. One type of problem basically says, here is some parameters that you have right at this instant in time, right? Always look for that kind of language. Say, at this instant shown, right? What you can do with that is you can sort of imagine taking a snapshot right then, right? That you don't have to think about how does it move from there. You can take that position that it's in. You can take the velocity at that position at that time, right? And you can just analyze that one instant of time, all right? The other variety that you see in dynamics courses are the ones where there's some finite stretch of time over which motion is allowed to happen. And as that motion is happening, you can actually calculate how it progresses through space. And those are typically a little bit tougher. They typically require that you do things like differentiation or integration to come up with functions to have the motion, all right? And we'll do a problem like that next after this problem. Okay? So at this instant, the radius value is 2 meters. The radius value is growing shorter at a velocity of 0.5 meter per second. That's what the negative means, is that it's growing shorter at a speed of half, I should say, a meter per second. All right, then we have the acceleration being 1 meter per second squared. That means even though the velocity is causing that radius to become shorter, it is accelerating, meaning that speed, drawing in is not as fast a moment from now as it is now. And if you let that continue on, then it would actually, at some point, turn around and start letting length out on that radius. Does that make sense? So it's being drawn in right now because it's negative. But since the acceleration is positive, it means that if you would allow it to keep moving over time, it would allow it to kind of go back outward, right? That's one of the ways to mentally interpret the signs of the, R dot, and R double dot. Okay? At this instant, theta is equal to 50 degrees. Theta dot, which is sometimes called omega, that's an angular speed or angular velocity, is 70 degrees per second. Keep in mind here, this says clockwise is positive, right? So that means that 70 degree per second is also clockwise positive. All right, and then lastly we have theta double dot, which is an angular acceleration. Sometimes the variable that's used for that in some text is alpha, lowercase alpha, and that is going to be 10 degrees per second squared. Again, that is positive, so all three of those are positive. Okay, and positive, remember, is clockwise. The last thing we've got is that there's a little collar that is sliding on a rod. The little collar I've labeled B down there. That rod is horizontal, and the little collar, the position of the collar relative to a position directly below the pivot point for the particle, that position is described with variable x. X is equal to 1 meter. X dot is 3 meters per second squared. This is positive rightward based on how I've drawn x right there. And then x double dot is going to be negative 2 meters per second squared, meaning it has a velocity to the right now, but it's slowing down, right? That's the physical interpretation of that negative sign on the acceleration. All right, so what we need to do is find the velocity of b relative to a, and the acceleration of b relative to a at this instant, and also find out what the magnitudes are of those two vectors. And I really probably should have little vector symbols over the top of these because these are vector quantities. Okay, so far so good? So the first thing we need to do for this is to find the velocity of particle A. Okay, so the velocity of particle A, and we do have a little bit of help with this. Okay, there's a formula that we derived last time based on polar coordinates that says that the velocity of A will be equal to r dot times the unit vector in the radial direction, okay, plus r theta dot times a unit vector in this transverse direction that we label u sub theta. Okay? So what should we plug into that? R dot is negative 0.5 meter per second. So that one's actually pretty easy. Okay. That is multiplied by this unit vector in the radial direction. Okay. What about the transverse direction? Well, I have to plug in my radius value that I have right now, which is 2 meters. I then need to multiply that by theta dot. Okay, theta dot is 70 degrees per second. Typically, we don't like to use degrees per second for these. The reason why is that all of these formulas were derived based on the definition of radians, where you can relate arc lengths to radius values. And so we need these angular speeds to be in radians if we want these formulas to work. Okay, so what we want to do is take that and multiply it by pi radians per 180 degrees. Okay. And then I can multiply this by the unit vector in that transverse direction. Okay. So what I end up with here for the velocity of A is this one just stays the same, 0.5 meter per second times that unit vector in the r direction. Plus, let me go ahead and punch this in. I've got 2 meters times 70 times pi, okay, divided by 180. Which gives me 2.443. And that would also be in meters per second. This would be multiplied by that unit vector in the transverse direction. Okay, well that's all well and good, but here's the problem. In order for us to actually do the addition that we need in order to find relative velocities, that's what we're ultimately going for, right? V of B relative to A, or A of B, or acceleration of B relative to A at this instant, we need to have uniform, I would say, vector systems in place. And right now, it would be hard, it's not impossible, but it would be difficult for us to express the velocity of B in terms of this polar coordinate system. It's probably easier to convert what we just came up with here to a rectangular coordinate system so that we can do these additions of our vectors. All right, so what I want to do is take this velocity that I just found that's in polar coordinates and convert it into rectangular coordinates. And that's a good skill to know how to do, to go back and forth between polar and rectangular coordinates. So let me put that label over here, converting to rectangular coordinates. Okay, here's what that's based on. What we need to do is think about what do each of these directions mean, right? Where we have a negative 0.5 meter per second squared times unit vector in the r, or the 2.443 meter per second times the unit vector in the transverse. What I'll do is I'll set up a little coordinate system here with x and y. And on this coordinate system, I'm going to draw the actual directions of these speeds that I have, these velocities that I have right here. Okay. Here's what that looks like. We'll start with the radial direction. Okay. If I have a negative speed in the radial direction, does that go toward the center of rotation or away from it? All right, I would say that negative value there means it's going toward the center of rotation. It means the r is getting shorter, right? It has a speed such that r is getting shorter. Yeah, that's what the negative value means. What's it? At this instant, right. At this instant. Okay, so what I'm going to do is show that as a velocity going up like this, right? And that velocity, I'll go ahead and I've shown it the actual direction it's going, so I'm going to strip the sign off of it, right? So this is an actual positive 5 meter per second, 0.5 meter per second, because I've shown it going the direction that the negative 0.5 meter per second implies. Does that make sense? Okay. Now this transverse direction is perpendicular to this, and what this positive number says is that is a speed that's implied if you have an increasing theta, right? That's the positive part of it, is an increasing theta. And since I'm taking positive to be clockwise for this problem, that means that this speed is going perpendicular to this other one down like this. Okay, and what magnitude does it have? Well, 2.443 meter per second. Okay, so this is part of it. The next thing we want to do is establish how do those directions relate with x and y, right, at this instant. Again, remember, all of this stuff that we're doing here is at this instant in time. Okay, so at this instant, given the fact that we were at theta relative to horizontal to establish the radial direction there, that radial direction can be established actually kind of with a line that goes along here, right? That's the radial direction, is along that line. Okay, and how does that line relate to positive x? Well, it is 50 degrees based on where theta was defined and what value theta was defined to be up here. Okay, well, if that's 50 degrees, we can use one of our geometry tricks that we know, and we can say that this must also be 50 degrees. Okay, this is what principle? You might remember this from geometry, or you might not. These are called alternate interior angles, right? They basically, no, this is not with this one. These are, yeah, maybe so, adjacent angles. Anyway, but you can see there, geometrically, those have to have the same value to them, 50 degrees on each side of that. Okay, so if that's 50 degrees, where else do you think I might be able to define a 50-degree angle? Okay, given the fact that x and y are perpendicular to each other, and the 0.5 meter per second squared and the 2.443 meter per second squared are perpendicular to each other, they have to rotate the same way, which means that this must also be a 50-degree angle at this instant. Okay. Well, how does this help us? Well, what we ultimately need to do is figure out the sum of these two velocity vectors that act in the x and the sum that acts in the y, which means we have to pick off components of these vectors that go in those two directions. So if I'm going to pick off, let's say, the x components of these two, all right, say, you know, I guess what we could call this is, I'll just call this the velocity at A, but we're going to write it in terms of I and j components instead of, you know, r and theta components. Okay, so what I'll put in here is the components that are going to be multiplied by I. Okay, and to that I'll add some components that are going to be multiplied by j. Okay, so first let's look in the x. 0.5. Does it go in the positive or negative? Negative, right? Relative to the x that I have defined right there. So it's going to be negative 0.5 meter per second times what trig function? Okay, remember, cosine goes with adjacent and sine goes with opposite, right? So we have to look at this and say, is that 50-degree angle measured adjacent to x or opposite of x? Right? Because we're dealing with x because we got this I component which is associated with x. Okay? And I would say it's adjacent, so we would have this thing times the cosine of 50 degrees. Okay, to pick off the component of the half meter per second squared that goes in the x direction there. Okay, but the other one, the 2.443, also has an x component. It is also negative. Okay, but I don't want the entire thing. I just want the piece that's pointed in that x direction. And to pick that off, I need to use sine or cosine, you think? Okay. Again, that angle, is it measured, you know, to where x is the adjacent axis, or is x the opposite axis? opposite, right? So we're going to use sine instead of cosine. Okay. And we can kind of do a similar thing in the y direction, right? 0.5 has a positive y component, so I put a 0.5 meter per second. I want not the adjacent component, but the opposite, so I put in a sine 50 degrees. Okay. And then the 2.443 has a negative y component. Okay. And to get just the component of that that goes in the y direction, you'll notice that this 50 degrees is adjacent to the y. So I would use a cosine function. Okay. And I'll spare you the boredom of typing these into the calculator. What it comes out to be is VA turns out to be negative 2.193 meter per second I, okay, minus 1.187 meter per second J. Okay, and that's kind of a significant result. So the next thing I want to do is, what if we state the velocity of B as a vector? Because now we have the velocity of A expressed as a vector, right? So that's helpful. Velocity of A is expressed as a vector, and it's a vector in x and y. So if I can express V as a vector in x and y, then I should be able to just add them together, right? Or, you know, do whatever math is necessary to come up with velocity of B relative to A. Okay, here's what that looks like. Okay, so this is expressing VB. Okay, I'll put here as a vector. So VB, does it have a vertical component to it? Okay, I'd say not. It's sliding on a horizontal rod, right? It has no vertical motion component associated with it. And so to express this, we would just have the velocity of that part, which is 3 meter per second, right here, 3 meter per second, I. What about J? Nothing. Okay. Now, how do I express my velocity of B relative to A? Well, keep in mind, what we started with was that the velocity of B is equal to the velocity of A plus the velocity of B relative to A. Okay, if we rearrange this, what do we get? V of B relative to A is going to be equal to velocity of B minus velocity of A. Okay. So all of that turns into this. The velocity of B relative to A is going to be equal to 3 meter per second minus a minus 2.193 meter per second I. Guess I'll do all this in one line. Okay, plus, here we do 0 minus a minus 1.187 meter per second J. Okay, does that make sense? We're just adding like components to each other. And I guess in this case we're subtracting them, but same idea. And so this tells me that the velocity of B relative to A is going to be equal to 5.193 meter per second. Okay, this is multiplied by I plus 1.187 meter per second J. Yes, sir.
When you drew that diagram and you drew your transverse vector.
Yep.
And I know that clockwise is positive, but it just seems to me that it come from the first quadrant. So how do you measure, or how do you know it's going in that quadrant?
Okay, so the question is, how do I know that the transverse component of the velocity right here is going the direction that I drew it on this diagram? And so here's how you can look at it. If this ball is swinging in a clockwise direction, right? It's moving down and to the left, right? If it's moving in a clockwise direction, right? That is the direction associated with a positive angular velocity. If it's swinging such that it's going in a clockwise direction, the velocity of this ball will go this way, right? That's literally at this instant the direction it's traveling due to the swinging action around the center of rotation. Good question. Okay. All right, so that's our first one. Are you curious about the magnitude of this vector? All right, I would be, because this, if you know the magnitude of the vector, that would be if you were riding, for instance, on A, and you wanted to know how fast it looked like B was moving away or towards you, right? How fast it was moving. Then you would want to take the magnitude of this vector, because that would be what you would actually observe as far as the speed at which that body was moving, either away from you or towards you. Okay, so what you would do is you would just take the square root of the sum of the squares, right? 5.193 meter per second, that would be squared, plus 1.187 meter per second squared. Okay, and if you punch those in, you will find that it looks like that magnitude is 5.327 meter per second. Isn't that great? Well, we're done with the easy one. Okay, this is the velocity is actually fairly straightforward. I mean, acceleration is not that much worse, but it is a little bit more involved to go with the acceleration, because finding the acceleration of ball A involves a little bit more effort. So we'll get into that next. Okay. So without further ado, let's do that. Finding acceleration of A. Okay. We also have a really nice handy formula that we made last time for this. The acceleration involved in in polar coordinates can be found with a few different components. First of all, there's two components that happen in the radial direction. The first one involves a literal acceleration of how big the radius is. That's r double dot. The next one is what we'd call the centripetal effect. Okay, and that would be r theta dot squared. And these are in this direction of the radial direction. Okay. To this we are going to add there's another effect that is basically due to the angular acceleration. So you take that and multiply it by r to get that effect. And then we add to that the Coriolis effect. So 2 times r dot times theta dot. And we mentioned last time that is basically the acceleration associated with moving to a faster position when something's rotating. Okay, so that's our starting point. Let's go ahead and start plugging some things in. So A of ball A. What did I have for r double dot? R double dot was 1 meter per second squared. Minus, my value for r was 2 meters. Oops, not quite done there, am I? 2 meters needs to be multiplied by theta dot squared. So theta dot up here was 70 degrees per second. Okay, that's 70 degrees per second. We would multiply this by pi over 180 degrees. Okay. And then that needs to be squared. All right, and all this would be in the radial direction. Okay, for the next one, I think I just found that radius value was 2 meters, right? So I can use that again. 2 meters times theta double dot. So theta double dot was 10 degrees per second squared. And that is going to be multiplied by, again, pi over 180. All right. So then we need to add on to this if we have a Coriolis effect. Okay. So we add on 2 times r dot. All right. I don't think we've used r dot yet here. So I go up here and r dot is negative 0.5 meter per second. Okay, and then lastly, I think I did use theta dot. It was 70 degrees per second times, again, we want to put in here pi over 180 degrees. And I believe that's all of my terms that I have for my, my transverse direction. So I multiply this all by that unit vector in that transverse direction. All right. Still not too bad, right? Just had a couple more terms to deal with. So now what we want to do is actually find those values. Again, I'll spare you the boredom of punching them in the calculator. Hopefully you believe me that I got these values correct. I've got negative 1.985 meter per second squared. Okay, and that's times that unit vector in the radial direction. And then I have what comes out over here is a negative 0.8727 meter per second squared, and that is in that transverse direction. Okay. So an interesting thing there that I can probably pick out, it looks like that centripetal effect dominates the tendency that the radius is actually getting longer, right? Or is the radius getting longer? It's accelerating longer, right? So it is accelerating outward, even though the velocity is inward, right? Accelerating outward, but the centripetal effect is dominating that effect. Okay, so it's actually the overall acceleration is toward the center, meaning that that turns out to be a negative value. Okay, for the other one, it means that even though the velocity is clockwise, the acceleration is counterclockwise, right? That's what that negative value means for the negative 0.8727. So it kind of means even though the velocity is going clockwise, it's slowing down in that direction. Okay? All right. Again, we need to take this and convert it into x and y components if we're going to figure out these relative velocities. Okay, so again, say converting to ij components. I'll do it kind of the same way we did before. Let's interpret what these are on an xy set of coordinates. Okay. Radially, again, I have a negative value there radially, which means that that value is again pointing basically the same way as the 0.5 was last time. It is, and the value there is 1.985 meter per second squared. Okay. Remember, clockwise is positive, and now I have a negative value that's given here. That means it's going to be opposite the direction that clockwise would imply. So that means now this vector would point this way, because as we just went over, clockwise implies that direction we had last time. Since we have a negative value, it implies counterclockwise, and that would be associated with that direction. And so this would be that 0.8727 meter per second squared. All right. So again, we probably want to do like we did last time and identify this is the line along which that velocity runs, and this angle down here was 50 degrees at this instant. Okay, and if that angle down there is 50 degrees at this instant, it means if I extend my x-axis back like this, it means this angle right here is 50 degrees at this instant. All right, and if that one's 50 degrees, and if we have two velocity components that are perpendicular to one another, it means that this must also be 50 degrees right here. Okay, and so now based on these, I can come up with my x and y components, or I guess I and j components, however you want to say it, of this acceleration vector. Okay. I'll do it kind of the same way I did last time. Okay, I'll start with this 1.985. We'll look at the x direction on that. So I have 1.985 meter per second squared. To get just the component that goes in the x direction, I need to multiply by the cosine of 50 degrees. Okay. The other component looks like it ends up being positive, so positive 0.8727 meter per second squared. Okay. This times the sine of 50 degrees. So I've got all of that, and then the direction is in the I. To this, I add all the stuff that happens in the vertical direction. So for that, I have 1.985 meter per second squared times the sine of 50 degrees plus 0.8727 meter per second squared times the cosine of 50 degrees. All right. And if you punch these in the calculator, what comes out is we have negative 0.6076 meter per second squared, I, all right, plus, here we've got 2.082 meter per second squared, J. I don't know what happened here. I thought I put a negative sign right there. That should be negative in that x direction, right, for the 1.985. I don't know if I erased it again or what, but anyway, that should be a negative right there. All right. So that's my acceleration of A. What about the acceleration of collar B? Okay, we'll go back up and look at the picture again. How can B accelerate? What direction can it accelerate? Okay, it's entirely constrained to move just in the x for collar B, right? So it only has a B component of acceleration, and it's given right here with x double dot, with negative 2 meter per second squared. All right. So what we find here is that the acceleration of B is going to be equal to negative 2, I said, right? Meter per second squared, I plus 0j. Okay, and that means that the acceleration of B relative to A is going to be equal to minus 2 meter per second squared minus, okay, a minus 0.6076 meter per second squared. Okay, and all of that is the I component. And then the J component is 0 minus 2.082 meter per second squared J. And what I'm applying here, just to make sure we're clear on this, what I'm applying is this relationship that the acceleration of B relative to A is the acceleration of B minus the acceleration of A. And so that's the principle that I'm applying to get this. Okay. All right. And this ends up giving me negative 1.392 meter per second squared I minus 2.082 meter per second squared J. Which is our answer. Okay, and if you're curious, the magnitude of this, which again you get by just doing the square root of the sum of the squares, comes out to be 2.504 meter per second squared. Okay, physically, how do we interpret that? Okay, we're saying this is the acceleration of B relative to A, right? Does this kind of make sense? So what it says is like from B's of B relative to A. From A's perspective, what does it look like B is doing, right? And again, you assume that the coordinate systems aren't rotating. So if you have non-rotating coordinate systems and you just have pure motion happening, and you're standing at A, what does it look like B is doing, right? That is what the interpretation is of a thing like this. These kinds of problems are actually, become very useful if you're trying to get two moving things to sort of sync at a certain time. Because what you want to see happen in order for, like, let's say you want to merge with traffic, right? What you want to have happen is by the time you get to the bottom of the ramp, right, and you get ready to merge with traffic, you want for your velocity to basically, the velocity of you relative to the other traffic, you want it to basically be zero, right? But it doesn't start out being that way because you're starting out here where your velocity is very different, but as the traffic moves, you get in line with them and you want for that velocity to end up matching, right? So this kind of thing is useful often in those kinds of problems where you need to know or you need to try to achieve a particular relative velocity between two things that are moving. All right? Or acceleration in this case. All right. Questions on that problem? Ready for another one?